In this unit, we're going to talk about uniform circular motion, or as I like to think of it, how to accelerate without really trying. When we get to work, you're going to think that's hilarious, okay? How to accelerate without really trying. Uniform circular motion is really a special kind of acceleration. But first, let's just look at some uniform circular motion. Here's our big bowling ball pendulum, and it's hanging from the ceiling like a pendulum, but if we move it like this, it's essentially going in uniform circular motion in the XY plane, this plane, right? There it goes. So let's draw that motion and see what it looks like. I would just draw it. I would just draw a circle like this. There it is. And I'd say at some point, the ball, as though we're looking down, is right here, right? So it's going around like this. So if I had to start drawing sort of the values or the vectors on it, I'd say it has some velocity, and at that moment, it's going like that, right? So let's now think a little bit about this motion. How would we describe it? Well, one, what does the circular part mean? It's going in a circular path. So surprise, surprise, uniform circular motion means it goes in a circle. But it's the uniform part that's really interesting that we want to talk about. What that means is it has a constant speed. All right. A constant speed. Does it have a constant velocity? No, because the velocity vector is changing direction. Constant speed, not velocity. And the speed we'll just call v. And I won't put a vector symbol on it because it's not a vector. It's just the magnitude speed. So what is interesting, though, is here the velocity vector looks like that. Here, the velocity vector looks like this. So what we can conclude is that there's a change in velocity direction. And basically that counts, if we're keeping score, as acceleration. So in 1D kinematics and what we've done so far, acceleration always meant the magnitude of the velocity vector was increasing. But this is completely different. Here the magnitude is constant, that's why we call it a speed, but the direction is changing. Any change in acceleration, any change in velocity counts as an acceleration. So if it's changing direction, that also counts. So now we want to think, how can we characterize this acceleration? So it's a little tricky. One way is to go back to your definition of acceleration and say A, the vector, is delta v, the change in velocity over delta t. So we could say over delta t, it's v final minus v initial, right? That's what it should be. So we talked about before. So what we can do right now is pick two times and label them v final and v initial and just see if we can figure it out. So here's the center. Let's look at it here when it was going like that, and here when it was going, let me draw it a little more precisely, like that. And we'll call this v initial and we'll call this v final. All right? So the vectors should be the same length, they're just going a little bit of a different direction. And to do that, then, we just have to literally do this vector sum. We have to say, let's draw the vectors now sort of independent of the circle. So we want to do VF minus VI. So I'm going to draw VF like that. There's the VF vector. And then I'm going to add head to tail the negative of the VI vector. That's how you would subtract VI. So VI is pretty much flat, but we're going to change its direction kind of this way, like that. And therefore, VF minus VI, if you divide it by a constant, makes the acceleration. So this has the direction of the acceleration vector right there. So if you look, you see the acceleration in this average time is like this. So the acceleration, when you're changing the velocity's direction in a circle, points in. Right? This is A. And for uniform circular motion, we give it a special name. It's called the centripetal acceleration. So centripetal, I believe, means center seeking, right? So as this thing moves around, the acceleration is always pointing to the center of the circle. That's why it's called that. So the centripetal acceleration, it's usually a with a little c subscript, and it points to the center of the circle. And also another way to think of it is that it is perpendicular to the path. That's another version of it we will talk about. Let's see, what else can I tell you about it? So let's now look at a little bit of motion here. Let me get the thing going in a nice circle again. So here it is. Here's the ball going in a circle, pretty good circle. So now if we want to think which way is the centripetal acceleration, it's always pointing in, right? So here it is pointing towards me. Right now it's pointing to the right. Now it's pointing in. Now it's pointing left. The velocity is always pointing with the motion. Velocity is always along the path. So velocity this way when it comes by me, centripetal acceleration that way when it goes by me. So now you know the direction of the centripetal acceleration. You also need to know the magnitude. I mean, if it's just a change in direction, does it have a value in meters per second squared? The answer is yes, it does. Even though it's not a change in the magnitude, just a change in the direction, it still has a value, and it's equal to this. AC, the magnitude, is the speed squared over the radius. If we give the circle a radius r, it's v squared over r. And you probably want to know where that comes from. And I'm just not going to tell you. It's too complicated and not worth it and weird and confusing. So just trust me, it's v squared over r. You really got to know. I mean, okay, here's how you can get it. It's very complicated. It's very unsatisfying. But let me show you how we can do it. So let's erase some of our definitions here. If you really got to know the magnitude, you can kind of think of it like this. I'm probably going to need a new drawing, but you asked for it. So let's imagine here we got our circular motion like that, and let's put it on a Cartesian coordinate system like this, where that's plus x and that's plus y, just because that's how my notes are. Okay, and I'm doing this, so I get to do it how I want. And let's pick a point in time like right here. There we go. So at this point in time, oh no, let's not pick that point in time. Let's pick maybe there, right? So there's the line to the center. There's the radius r, right? What else have we got here? We could also describe this thing's x and y position with this triangle. See, it's over this far in x and it's up this far in y. So there's a little right triangle. That's exciting. We could also describe its velocity vector, which I chose to say is this way. That's the velocity along the path. And we could also get its x and y components of the velocity like this. There's vx, and there is vy. I told you didn't want to look at this. You think you know better. Let's see, so this we'll call theta, right? This is theta, then this is theta, according to my 7th grade geometry teacher. And if that's theta, then this is theta, according to Mr. Reed, my 7th grade geometry teacher, when we learned all the angle, side angle stuff. Okay, so now we have this whole setup, and you can kind of see there's a relationship between the angles and the x and y components of the position and the x and y components of the velocity. Right? They're related by doing a bunch of geometry. So what we could do now is we could do some similar triangles, right? So we could say something like the x component of the velocity is to the velocity as the y component of the position is to the radius. What? Let's see, does that make sense? So the x component of the velocity is to the total velocity as the y is to the radius. See how those are similar? I should have done the other one first. The y component of the velocity is to the velocity as the x component is to the radius. You can see this one better because the theta is there, right? The y component is to this as the x component is to that, right? Similar triangles, or the sine thetas are the same or something like that. Right? So we could say that. All right, that's somewhat amusing, I guess. And then we could also say, let's now write the velocity using those components. Okay, we could say that the velocity vector, therefore, is equal to, let's see, the velocity, let's see, yeah, so we could say that Vx component is v times y over r. The speed times y over r, I hat, plus the y component is v times x over r j hat. And you say, wait a minute, the x component depends on y and y depends on x? Yes, because it's moving in a circle. This isn't some silly straight line motion. This is now complicated. Okay, so what is acceleration? Acceleration is the time derivative of this. So let's take the time derivative. The v is constant uniform motion, constant speed. V is constant, r is constant. V over r, pull those out. Take the derivative of y. What's the derivative of the y position? Vy I hat. Plus v over r is constant. What's the derivative of the x position? Vx, x. J hat. It almost looks like we're describing the vector, except look, Vy is on the I hat and Vx is on the J hat. What does that mean? That probably means that A and V, that the acceleration and the velocity vector are not in the same direction, right? If these two things depend on each other. So let's not worry about the direction. We've already done the direction. But let's now get the magnitude of this. The magnitude of this A is the square root of this squared plus this squared. So the V over R comes out, and the square root of Vx squared plus Vy squared, even though they're in the wrong place, is still V. Right? So the V from the Vx and the Vy multiplied by that V is V squared over R. And you say, hey, it's a centripetal acceleration. I'll put a C on it. See, I told you didn't want to see that. I told you. If you keep studying physics a little bit longer, you'll eventually get to the important concept of periodic motion. If I had to define periodic motion, I'd say something, a motion, clearly, that repeats every t seconds. T seconds, where t is the period, how long it takes to go around. So vibrations are periodic motion, waves are related to periodic motion, but here circular motion also is periodic motion. So we take this opportunity to kind of introduce you to the idea. Right, so here the bowling ball is still moving in uniform circular motion. So the period is literally how long it takes to go around. So let's time it. 1,000, 2,000, 3,000, 4,000, 4 seconds. So the period here is 4 seconds. If you want to calculate the period, you would have to have some uniform circular motion going with some radius r, some mass going around like we just showed you, like we have going on over there. And you'd say, so if you have a circular with radius r at v, let's calculate the period. Well, let's see. It's really just kind of like one-dimensional motion if you think about it. It's how far it goes and how fast it's going. So d equals vt, so t must be d over v. So how far is it going when it goes one loop around? It's going one circumference, so 2 pi r. Oh, and I called it big R or little r? Let's call it little r. 2 pi r over how fast it's going, v. The speed in this case. We're not doing vectors. 2 pi r over v. So that's how you find the period from a general sort of circular motion problem. But another parameter we like to think about is not just the period, but a new kind of speed, basically the angular speed. If you wanted to characterize how fast this thing is going in a circle, you could go with the period. You could say if it's going really fast, the period is really short. But the more natural thing to consider would be how much angle does it go through per unit time. And you know, if you were raised in the British degree system like I was, you would think of it 360 degrees is all the way around. So you'd ask yourself, how many degrees does it go per second, right? But that's not really what we do. We like to do it in, so this is the angle per second in radians is what we like to use. So instead of 360 degrees all the way around, we say 2 pi radians all the way around. So we call this thing omega, and how many degrees per second? Well, we know it goes all the way around in 2 pi. So we say, oh, okay, it goes 2 pi radians, that's a full circle, in t. Right, so the relationship between omega t is pretty simple. Omega is 2 pi over t, t is 2 pi over omega. So this is called the angular speed. Okay. So two important parameters of circular motion that problems will want you to think about. you now have all the formulas you need to think about omega and period, but I want to show you a different way to remember them that makes it a little bit easier. There's an interesting way that they kind of come together. So we're just going to look, we're going to go between angular, omega, and period, or angular velocity and period, omega and t, to just the speed and the acceleration, the centripetal acceleration, which isn't really translational, but you know what I mean. Omega t and v and a. So here we have, as usual, an object going in circular motion with some radius r, and it's going here at some speed v. That's what the whole unit almost is about. So first let's look at the speed. Right, we had this formula, we said omega is 2 pi over t, but then we did have t written in terms of the velocity. What was t? It was 2 pi r over v, right? T was how far it has to go, the circumference, over v. So you actually see in this case the 2 pi's go away, and you can see an easy relationship between the speed and the angular velocity and the radius. It's always just, they're always related by a radial, by an r. And they kind of need it. If we think about units, of course this is in meters per second, right? Omega, we said we have to do it in radians, so it's in radians per second. But radians aren't really real. It's kind of a natural angle that has no physical quantity. This is really just in 1 over seconds. So what would it take to get this from just 1 over seconds to meters per second? Another meter. So if you can't remember if it's v equals omega r or omega equals vr, well, first of all, just remember it's v equals omega r. But the units can always get you there. It's the omega that needs another meter to become meters per second. So I just found this easier to remember than all of the omega and all the t formulas. We can also do it with the centripetal acceleration. Centripetal acceleration. All right, and we can say, what was it? AC was v squared over r. But then we could say, oh, but v is just omega r. All right, so that must be omega squared r squared with an r in the bottom. All right, so then we see that the centripetal acceleration AC is just r omega squared. So here, yeah, it's like that. So omega squared r, v is omega r, AC is omega squared r. And again, the units work out. This would be 1 over second squared. So this is meters per second squared, same as that. So just for sort of doing problems quickly, especially like on an exam, I find those two useful to keep in mind. There are similar ones later when we get to rotational numbers. Let's do a few actual numbers here. I think we could with our demo. We have our bowling ball here, slowed down quite a bit. But if we bring it out to a radius of about a meter and send it around, we already measured that it went around in 4 seconds. Right? Our period was 4 seconds. So we should be able to figure out its velocity. Let's see. So its velocity as it goes around, the radius is 1 meter. Omega, we remember, is 2 pi over t, so 6.28 over 4. That would be the velocity. 4 seconds, meters per second. What is that? 4 goes in, ooh, let's do the long division, because I know you're on the internet to watch me do long division. 2 left, 22, 5. 1.57 meters per second. That's how fast it's actually going. Exciting. But what about the acceleration? It's easy to visualize the velocity. Yeah, that looks like about 1.5 meters per second. What about the acceleration? You're not used to watching things accelerate. So this will be exciting. Let's see, what is this equal to? Omega, that was that 2 pi over t, right? And that's squared and times 1, but the t was 4, and this was 6.28. So we can see numerically, it's actually this answer squared. See, I said that was 1.57, and it's not always just squared, it's because this only gave a 1, right? 1.57 is like 1.6, and I believe 16 squared is 324. So I'm going to say that it's 3.24 meters per second squared. So if you ever wonder what 3.24 meters per second squared looks like that. So now we're going to abandon uniform circular motion and just talk about any curvy motion and how we think about the acceleration, because this really freaks people out. Okay, we break the acceleration into tangential and radial components, and doing that really bothers people. So first, let's just talk about the physical motion. So here we have a track and the ball is going to go down and make a loop. Okay? We're going to talk about this in great detail later. What forces does it take? How fast does it have to go? But right now, the only reason I want to do it is to realize that as the ball goes around, it'll be going through a circle, but it's actually going to slow down and speed up. Right? As it tries to go up, it's going to slow down. As it comes down, it's going to speed up. So it's not uniform circular motion. Let's watch it go. So maybe you could even get a sense that it was slowing down here, speeding up there. Let's watch it one more time. Okay, so let's describe this mathematically. So let me draw roughly what you just saw. This comes down and it goes into a circle like that. The ball goes around and it is moving in a circle, but it's not uniform circular motion because we know the ball is going to slow down and the ball is going to speed up because of gravity, which we'll get into all that later. But the idea is we want to break this now complicated acceleration into two components, radial and tangential, right? So A is really just the sum of the radial acceleration vector. So this is radial. It's like the centripetal and plus the tangential, AT. Tangential. And it's kind of like 1D. It's the speeding up. Or it could be the slowing down, right? If the thing is, so it's slowing down this way, speeding up that way. So people kind of panic about this, but one thing to realize is that these are always perpendicular. The two components are always perpendicular to each other. What we're really doing is simply breaking the acceleration up into two components, just like if we were doing it in x and y. This is equivalent to saying the acceleration is ax I hat plus ay j hat. It's really the same thing. We could even call it AR R hat, AT T hat. But if we make up new unit vectors, people freak out. Right? So instead, we just call it the sum of these two perpendicular vectors. But it's exactly the same thing. It's kind of like a little Cartesian coordinate system is moving around with the ball and rotating as it goes along the track. In uniform circular motion, this one is called the centripetal acceleration, and this one is 0 because you don't change your velocity in uniform circular motion. So to find them in sort of a problem, if you had to do a problem and it said find them, one thing you'd want to remember is I said this one is kind of like AC. Basically, it's equal to the negative of AC. And really this is just has to do with which way you consider positive. So if you're talking about motion, in this case it's actually a circle, the radial direction is positive that way. The center-seeking direction is positive this way. So it's the same magnitude, it's just one you call it positive out, and one you call it positive in. So if something is going in a circle and you calculate its magnitude of its centripetal acceleration, it would be a positive number if you're calling it the centripetal acceleration. It would be a negative number if you're calling it the radial. That's really the only difference. The magnitude is the same. So the magnitude of AR is just like the magnitude of AC, except we put a negative sign in front of it. V squared over R. Why the negative? Because if you're going around a circle, we showed with the vector diagrams that the real acceleration point's in and the positive radial direction is out. So you need the negative there. Okay. What if you want to get tangential? Well, to get tangential, it's really just the magnitude is actually the old dv dt. The tangential velocity, how fast it's going. It's the rate of change of the speed along the tangential path, and the direction is along the path. The direction is along the path. I wanted to show you this one more time because it's a great way to visualize tangential and radial acceleration. So let's watch the ball make its way through the loop. Here we go. And you can see we're going to freeze it in a couple of places and we're going to analyze the acceleration. So at this side you can see it's slowing down because it's going uphill. So the radial acceleration is, of course, towards the center, but the tangential acceleration is down because it's slowing down. Over here on the other side, it's speeding up down the loop, and the radial acceleration is still towards the center because it's radial, but the tangential is now pointing down.